Okay. Homework 2, Part C, Part 1. We have a flow rate of 1 moles a second. Mole, we know the mole fraction, we know the distillate composition, and we know distillate recovery of about 90%. So we're going to go ahead and derive some equations to solve for distillate, bottom flows, and composition. And compositions, yeah. So we can go ahead and go here, and we have a feed coming in, and we have F, and we know the so we know the flow rate, and we know Z right here, and we have two things coming out right here, which at the bottom would be our bottom, and then our XB is be our bottom leaving, and then we have our distillate up here, and we have XD right here. So we're gonna go on and kind of derive some of these equations, and we're gonna start with the distillate flow rate right here. So and we also know our D, which is our recovery rate of the distillate. So we're gonna start with our distillate here. So we have D, and then we're gonna times it by our liquid composition, or a liquid mole fraction, and then it's going to be equal to our feed times Z, which will give us the liquid mole fraction, and then times our recovery rate, D, or R. And this is what that's going to be equal to. So then we just solve for D to get our distillate flow rate, and that's going to equal F Z R D over X D. And that's the derivation for how we find our flow rate if our knowns are feed, Z, our composition of the feed, and we know recovery rate, and our composition of our distillate. So next thing that we're going to figure out is how we get our flow rate of our bottom. So in order to do that, we'll do an overall mass balance where F is equal to D plus B, and then we just rearrange it around. Pretty simple. So it's going to be B equals F minus D, and that's, we know F, we know D, so then we can solve for B. So now that we know B, solving for XB will be pretty easy. We kind of just use what we did up here, except we're going to have to change our recovery rate for the distillate to our recovery rate for the bottom, and our recovery rate for our distillate plus recovery rate from the bottom we know is going to have to equal 1. So it's kind of like our feed quality. It's just going to be 1 minus our RD. So we're going to have B times X B equals F Z 1 minus R D. And then we divide by XB, or by B, I mean, because we're solving for XB, we get F Z 1 minus R D over B. Okay, so this will help us when we move on to Python. We'll generate a McCabe field diagram using Python with these specific constraints that were laid out in homework 2, and these equations right here will help us solve for our unknowns and make it possible for us to make the graph. So we'll move on to that next. Okay, we're going to be working on the Python for homework 2, Part C, Part 2. So we'll go ahead and do that. So we have our volatility is equal to our 2.5, and then we're going to have our F is equal to 1, our distillate composition is going to be 0.95, so our XD equal to 0.95. What else are we going to have? Our Q, we'll say we have a saturated liquid, so it would be 1. And our other knowns is our recovery rate, so of our distillate. So we'll do RD equals 0.9. And then the next thing we'll do is our reflux. which we'll say is 1.5. Okay. I think that's all we need right now. Okay, so the next thing we can do is we can use the equations that we derived before in order to calculate our unknowns. So I have our paper here from before that we'll use. But first off, we also do need our x1s to equal. So np dot ln space 0 to 1, 21 times. And then we want our y1s. So we'll use our equation for before where we solved for our volatility right here. We use our volatility in order to derive an equation that solve for our vapor mole fractions. And that equation is our A times our x1s. And then we have this is going to be divided by our 1 minus x1s plus our alpha, and we have our x times our x1s. Okay. Oh, equal sign there. Okay, so that's our y1s. Okay, now we can move on to our back down to our unknowns that we solved for before. So we can solve for our distillate, which is D, and that's going to equal our feed times our Z, which I don't think we defined our Z yet, which is 0.55. Pretty sure. Yeah. Okay. So 0.55. So F times our Z times our RD. And then that's going to be divided by our XD, our mole fraction for the liquid at the distillation. Put parentheses around this. Okay, and then divide by our XD. Okay, so now we know our distillate, and like we said before, we know our distillate and our feed, so now we can solve for B. So B is just equal to F minus D. And then since we know our B now, we can now solve for our boil-up ratio. So that's going to be XB is equal to F, put parentheses, F times our Z times our 1 minus RD, and then divided by our B. Okay. All right, and the next thing that we can solve for is our well, that wasn't our boil-up ratio. That was our liquid mole fraction at our bottom. Now we can solve for our boil-up ratio that we're going to need later too. So VB is going to be equal to our R plus 1, and then times our D minus, or D minus our Q minus 1, and then times our F, and then divided by B. Okay, and we derived that also in a earlier video. Okay, so now we have all of our unknowns, so we can go back and we can do, we have our, I already set up our VLE, because we also did that in a previous video, where it was just big diad scatter our x1s and y1s from our Lin space and our y1s that we derived here, that give us our equilibrium curve, and then just from 0 to 1, 0 to 1, they give us our 45-degree line. So we'll add our rectifying line now, which is going to be x is equal to xd, and then this is going to be equal to 0, since we're just going to stop it at the y-axis, and then we're going to have y is equal to xd also. We proved that earlier in another video, that our our mole fractions are equal to each other at the start of the rectifying line, and that's why they meet at the 45-degree line. And then so we also solved in an earlier video uh, what y would equal. Actually, no, we didn't. But we can look at our rectifying line and see here that if our mole composition for our liquid, our mole fraction for our liquid is 0, it's just equal to 1 or xd over r plus 1. So just xd divided by r plus 1. And mode do equal lines. And then line underscore color is equal to green's fine. Okay, we'll go ahead and try this and see if our rectangle ends up right. Yep, all right, there's our rectifying line. Okay, and next thing we can do is move on to our stripping line. Underscore scatter x is equal to our xb. Except this time, we can't just have it equal 0. This time we can't just have it equal 0. So we solved this earlier with y we're equal to 1. That's what we're gonna have it stop at. So let me find that equation real quick. Well, okay, so yeah, here it is. So it's VB plus XB, VB plus 1, like how we derived earlier. So it's VB, put some parentheses right here. So so we have VB plus XB, VB plus XB, parentheses divided by our VB plus 1, VB plus 1. Okay, and then we can do mode equals lines, and then line color, line dot underscore color, yeah, blue's fine. Okay, and we can see if this works. He is not defined. I do shift enter up here. All right, yeah. So there's our. That should have stopped. Let's see what happened. Oh, I didn't define y. That would make sense. Y is equal to again our xb, and then this will be equal to 1. Shift enter. There we go. Okay, so yeah, stops at that 45, starts at the 45-degree line and goes up. So the next thing that we'll do is create our, and it doesn't pinch also, so that's good, you know, it's pretty close. So the next thing that we'll look at is our Q line. Okay, so now we'll look at the Q line. So we'll do fig dot add underscore scatter is x is equal to our composition, and then it's going to be equal to 0, and then we have our y. What should have been? Okay, and then we have our y, which is going to be equal to our C2 as well, and this is going to be equal. So we have derived it earlier as well, our Q line. So if we just set our x equal to 0, which is what we want, we can solve for what our y composition would be. So we just have z over q minus 1. So z divided by q minus 1. And then, oops. And then we have mode. Mode is equal to lines. And then line underscore color, we'll say is yellow. And oh yeah, so we have division by 0 right here. So we'll use EPS, which is like the lowest number possible. To not include right off there. So we'll just do Q minus 1. We'll put that in parentheses, and then we'll add EPS to it. So plus EPS. Okay, we'll shift enter. And you see that this is really big because the slope is basically almost straight up and down. So in order to stop that, we just do fig dot update underscore y axis and range from 0 to 1. And then we hit shift enter. So our rectifying line should cross here. So something went wrong somewhere. So I accidentally had set my reflex ratio to 1.5 instead of 2. So that shifted it over and made our Q equal or intersecting our rectifying and straight line. So we have our McCabe field diagram right here with our Q values, and we'll move on to. So the next thing we want to do though is create our steps. So the first thing we need to find is the x-intercept right here, because as soon as we pass here, we're going to be using our stripping line as our guide. So we have our x-intercept, and this is going to equal, we derived this earlier, so this is going to equal our negative xb, our negative xb divided by our vb, and then minus our xb divided by r plus 1. And then this is all going to be divided by r divided by r plus 1. And then minus our b plus 1 divided by bb. Make sure this all has parentheses around it. Okay, so enter. Okay, and then we're going to create like an open array for our y values. So we have, or for our steps, so we have x steps, and this is going to equal just open brackets, and then we're going to have y underscore steps. This is going to equal open brackets to create an array. Okay, and then we're going to do a for loop. So we're going to do for I in range, or for I in 100. Okay, and then we are going to, let me look at this again. Actually, these aren't going to be open brackets because we want these to be filled with XD. We want this to be filled with XD because this is where we want our steps to start, and they're gonna start at the beginning of our rectifying line, and then we want y underscore steps to equal y dot steps, or no, we want y to equal y dot append there. Okay, so no, I don't think that's right either. Hold on. Okay, yeah, okay. So sorry, I'm getting mixed up with my steps here. So y dot append, we don't want that. We want y underscore steps, and we want this to start at 0. So we want it to start at our at the first value here. Okay, and then so instead of solving for our y's here, we instead need to solve for our x. And the way we will do that is with the volatility that we have, how we solved for y before, we solve for x. And I won't show you guys just because it's basically the same thing we did in the earlier video, just solving for the x. So just y divided by our volatility, which is a plus y minus a times y. Okay, and then we want our x underscore steps to append, and then we want y underscore steps to append. Okay, or we don't need one brackets there. This will be x, and this will be y. Okay, and we don't want that down here. This should be a dot. Got a capital X. Oh, I just put a capital S here. Okay, there we go. That's savvy. Okay. All right. And then we'll go farther into the for loop. Okay, so we're gonna now do we do not want that. So we'll do our if statements. Dude. Okay, we'll do our if statements. So if x is less than our xb, we want to break it. So we're just gonna have break. Whoops. We'll break it. Okay. And then we're gonna do oh sorry. Right. So if x is more or equal to our x intercept, we're going to want to use our y is equal. So we're solving for our y's here. So we're going to want to use the rectifying line, that equation that we had. So let me find out real quick. So that's just going to be 1 plus 1 divided by r plus 1, or not 1. We'll do our xd. xd divided by r plus 1. And then this is going to be plus our r times x divided by r plus 1. Okay, and then we'll have an else right here, which is going to be, so if it's anything else, it's going to be past the intercept line, but in between, but not past the start of the stripping line, and we want it to end on the stripping line, which is why we have a break right there, because it's past that, we want it to stop. So, and anything else, our stripping line is going to be the driving factor here. So we'll use the stripping line equation. So that's going to be y is equal to our VB plus 1 divided by our, or it's going to be, yeah, So we'll do VB plus 1 times our XB divided by our, or this is going to be XJ, or just X, divided by X. And then this is going to be minus XB over VB. Okay. And then so then we're going to want to append these again, because if you don't, it'll either follow the equilibrium curve or just our stripping and rectifying line. So Control V, that should be back, enter. All right, so that should be good. Pen 9, yeah, get rid of that. Do a pen 9, I can't, oh, I copy paste it right here. Okay. Okay. And then the next thing to do is just plot them. So we're gonna graph these lines right here. So we'll do fig dot add scatter. Yeah, that's what we want. So and then we'll hit Control. Well, something went wrong with our steps, because past here is still using the rectifying line. So I'll go solve that. So we used a wrong equation for the x-intercept. So we're just gonna do this, and then we're gonna use this equation instead. So we have z divided by our EPS plus our q minus 1. And then we're gonna have plus our xd divided by our r plus 1, then divided by q divided by our EPS plus q minus 1, and then we're going to have minus r divided by r plus 1. Okay, shift enter. Okay, so there we go. Now our flip matches up with that, and let's try this again. Shift enter. Okay, all right, there's our diagram now. We have our steps. So next we'll move on to the next part. Okay, so I had the VB wrong right here. I had a capital VB, but now the stripping line is moving with our reflex ratio. But we set it to 0.8, and you can see that it starts to go above our equilibrium curve. So we start to reach a pinch there. So it's not possible for we lose our driving force. The next one, oh, hold on a sec. So the next one is 1.5 and 5. So this works out well. We just end up with more steps, kind of, because this line is a little bit shallower. This line's a little bit steeper right here. But we don't reach a pinch here, and we get past it. And then we can try 1 or 5. And you see right here, if we have a reflex ratio of 5, we end up with a lot less steps than we did with 1.5, and we still end here. So yeah, that's the video.